Hey guys, Mr. Dabrowski here. Just wanted to review this new topic of polarity that we've been talking about the past couple of classes. So we've done a couple assignments on this so far. We looked at the crash course video. We did that Bare Essentials comic strip, and then we looked at the applications of polarity in terms of soap and how that helps to clean a stain, a fabric, and also helps to destroy viruses, which is a very timely topic right now. Um, so I just wanted to make this video to review some of these topics with you and offer some further instruction. So reviewing this term for polarity. So polarity is the distribution of electrical charge in a bonded molecule. Okay, so when we're talking about the word polarity, think of the word pole, right? So when we're talking about the north and south pole of the Earth, you're looking at the northernmost and southernmost tip of the Earth, or the pole in a magnet works the same way. You have a north and a south pole, and that's how a magnet would work. So when you're looking at a molecule, depending on the atoms involved in the molecule, they could have a polarity, which could cause that molecule to change shape. Polarity is caused by differences in electronegativity, which we'll review in the next slide. So on this image you see here, this is an H2O molecule, so water. You see the oxygen in red, the two hydrogens in blue, and you see the arrow. The arrow direction is showing you which way the electrons are being pulled. Okay, so oxygen is pulling the hydrogens towards it, which would give oxygen a slightly negative charge and hydrogen a slightly positive charge. And we'll talk about why in a second. So like I said, electronegativity is what's determining polarity of a molecule. We talked about electronegativity last unit when we learned about the periodic table and the trends that the periodic table consists of. So electronegativity is the tendency of an atom to attract electrons towards it. Okay, it's the tendency of an atom to bond to something else. The atoms that have the highest electronegativity exist in the top right-hand corner of the periodic table. So fluorine is the most electronegative element. Okay, oxygen's a close second, and then your other elements here in that reddish color have the higher electronegativity. So the more electronegative an atom you have in a molecule that's bonding, the more likely that bond is going to be polar because that atom is going to pull the other electrons involved in that molecule towards it. So in terms of polar molecules, this word polar molecules means that it's a molecule that has an uneven distribution of charge. Okay, so polar molecules occur when the electrons in a bond are not shared evenly. And when we talk about polar versus nonpolar, we're only talking about covalently bonded molecules, not ionic bonds. Okay, so when you have a polar molecule, what that means is one side of the molecule is slightly positive and the other side is slightly negative. So taking a look here at HCl, which is hydrochloric acid, okay, here's the electron dot diagram for each, and then here's the bonding diagram. Okay, remember that's a single bond here. So this means that hydrogen and chlorine are sharing two electrons, which would give hydrogen here a full outer shell of 2, because remember, hydrogen can only fit 2 electrons in its only outer shell. And then these 2 electrons would fill chlorine's outer shell of 8. So these are covalently bonded. Okay, so taking a look here, um, this would be a good example of a polar molecule. So you see this diagram here is showing you here's an H, here's a Cl, and you see the direction of the arrow is showing you in which direction the electrons are being pulled. So this means that chlorine is pulling the electrons towards it away from hydrogen, okay, which would make chlorine have a slightly negative charge because it's more electronegative, okay? It's pulling more electrons towards it. And if you remember, electrons have a negative charge. So if it's pulling more electrons towards it, it's going to become slightly negative, okay? The reason, again, why chlorine is pulling the electrons is because chlorine's more electronegative, so it's going to pull those electrons towards it, but also chlorine has more free electrons around it, okay? And because electrons are attracted to each other, these electrons are going to want to go in the direction of the other electrons. So you see how these electrons in red are going to be pulled towards the chlorine, which has these free pairs of electrons here. Okay, so hydrochloric acid is a good example of a polar molecule because we have one side of the molecule which is slightly more negative and one side which is slightly more positive. There's an uneven distribution of charge. But I also want to talk about nonpolar molecules. Okay, so nonpolar molecules are molecules with an even distribution of charge. Okay, so that means that the charges across a nonpolar molecule are shared evenly. So if you take a look here, a good example would be CO2. So here's a Lewis structure for CO2. So you have one central carbon, you have double bonds to two oxygens on each side. Each oxygen has two free pairs of electrons. Okay, so just making sure this is a valid covalent bond, you would take a look at carbon here. It wants 8 valence electrons. It has 2, 4, 6, 8. Remember, each bond is 2 electrons, so 8 total. Carbon's good. And the oxygens are also full because 2, 4, 5, 6, 7, 8. So this is a good example of a covalent bond. CO2, carbon dioxide, is nonpolar. So here's why. Take a look at this diagram here where my cursor is. You see that you have a central carbon and you have an oxygen on each side. Okay, each oxygen, like you see here, has 2 pairs of free electrons. Okay, on either side. Oxygen, because there's one on each side, they both have an equal amount of electronegativity. This left oxygen is pulling the carbon an equal amount as this right oxygen. So think of it sort of as tug of war. Each oxygen here is pulling the carbon equally, which means that that carbon's not moving in one way or the other. Those electrons that are being shared between carbon and oxygen aren't going in either direction. They're being pulled equally, so they're not moving. Okay? So because the oxygens here have the same number of unpaired electrons and also the same amount of electronegativity, they're pulling carbon equally. This is a nonpolar, okay? Charges are evenly distributed. You have the same amount of negative charge on the right side as you do over here on the left side. So that is a nonpolar, an even distribution, okay? As opposed to the last slide where you had a hydrochloric acid, that was polar because the chlorine on the right-hand side had a more negative charge. So both sides were unequal. In this example, both sides are equal. You have negative on the left, negative on the right. Okay, so carbon dioxide here is a good example of a nonpolar molecule. So I just want to show you these images from that Bare Essentials comic strip, which you guys worked on last week. I think that this lecture is going to help clear up some of that if you struggle a little with it. So what I would suggest doing is after this lecture, go back and take a look through it because I think it's going to help you a little bit with this background. So let's start over here with our CO2. This is the exact molecule you just saw on the last slide. So this penguin is representing the carbon. The polar bears are representing oxygen here. The ice cream scoops are representing electrons that are being shared. So this is this is a non-polar molecule, sorry, because this polar bear, this oxygen, is pulling the electrons towards it. Same thing with the left polar bear. Both oxygen molecules here, guys, are pulling the carbon equally, pulling that poor little penguin equally to each side, just like tug of war. So this penguin, this carbon is not moving in either direction, is being pulled equally. This charge is being distributed equally. So that's why this would be a nonpolar molecule. Versus the right-hand side here, hydrochloric acid, are a good example of a polar molecule. So here we have Cl represented by the polar bear and hydrogen represented by the penguin. Again, ice cream is representing those shared electrons between them. So the polar bear here, this chlorine is pulling, as you see, pulling the hydrogen towards it, pulling the penguin towards it. The penguin's moving, the electrons are moving in the same direction as a chlorine, which means that this is a polar molecule. Okay, the charges are unevenly distributed. This chlorine, this polar bear, is pulling stronger, okay, making that hydrogen and its electrons move closer to it, making sure this would be a negative charge, giving this a positive charge. So hopefully that gave you some more insight into that comic strip if you struggled. What I would do is go back and take a look through it after watching this lecture. So that's all I had for you today. If you're still struggling with this topic, Take a look at the slides that I posted to Google Classroom. On the left-hand side, you have a couple good articles here that might help. And then I posted a couple good YouTube videos that might help you as well. But just take a look at the disclaimer on the bottom of the slide. If in any of these resources you see anything numerical or mathematical, you could ignore that. We're not so focused in on the math concept of this, more focused in on the balance of charges and being able to identify if a molecule is polar or nonpolar. Okay? So I hope this helped. Feel free to reach out with any other questions or concerns. Hope you have a good rest of your day and stay safe, guys. Thanks.